Hello and welcome. This is the key to practice quiz 14. So to three sig figs, what is the mass of one molecule of methanol? Okay, so one molecule of methanol would be CH3OH. So let's work that out. So that'll be 12.01 plus 1.008 times 4 plus 16.00. So that's 32.0 AMU per one single molecule. So 32 AMU is correct. 32.0 grams would be the mass of one mole. This mass here would be the number of grams. I'm guessing that's going to be the number of grams of one molecule, but in grams, not in AMU. So if we convert AMU to grams using the conversion factor that there's an Avogadro's number of AMU per gram, then the mass of one molecule in grams would be 32.00 AMU, and then divide by Avogadro's number, so divide by N sub A, number of AMU per 1 gram. And so if we were to do that, I'm just going to point out here that does work out to 5.32 times 10 to the minus 23, but that would be grams on AMU. So that's wrong, this is wrong, that's nonsensical. So the answer is A. The term that is used to indicate the degree of agreement with the true value is the definition of accuracy. I actually remember when I was putting this together, qualitative and quantitative sound good, but it's just the definition of accuracy is closest to agreement with true value. Quantitative and qualitative are like adjectives that you would use to describe data. So not exactly what the term accuracy is, how it's defined. Okay, so we have marijuana, number 3. So we're working out the percent, or the empirical formula from the mass percents of marijuana. Some of these problems should say by mass, but if not, these are just meaning the mass percents. I don't know how else we would solve the problem, but we just take the masses and try to convert those into moles. And so if we treat this as a mole problem, or like a relative mole problem, just convert these to grams and into moles. So I'm going to do that without writing this out. 76.4 divided by 12.01. That's 6.36 moles of carbon. I'm going to take the 9.2 divided by 1.008. That's 9.13. And then I'm going to take 14.5 divided by 16. That gives me 0.913. So this is definitely the smallest. This looks like it's going to be 10. So if I divide all these by the smallest and keep my ratio intact, then that will give me, let's see here, 6.36 divided by 0.913 gives me 6.97, which rounds to 7 moles of carbon as a ratio to, this would be 10 moles of H to 1 mole of O. So empirical formula here should be C7H10O. So the answer should be D. Lithium carbonate used to treat manic depression, it says. How many lithium ions are present in 0.1 grams of lithium carbonate? Okay, so let's say number of lithium ions is going to be equal to our mass of Li2CO3. Then we need to use the molar mass, number of grams per moles, because I'm going to go grams to moles to Li2CO3 units. Then I'm going to go to number of Li plus ions. This is my thought process here. So I need to go to molar mass. So I take lithium's molar mass, which is 6.94 times 2 plus 12.01 plus 16 times 3, 73.89 grams per mole of Li2CO3. There's a few ways. I'd say 1 mole of Li2CO3 contains 6.022 times 10 to the 23 Li2CO3 units. Kind of like a molecule, just not a molecule though. It's just units of Li2CO3, where one Li2CO3 unit contains 2 Li plus ions. So we're just taking 0.1, divide by 0.10, divide by 73.89, times Avogadro's number, and then 2 lithiums per unit. That should give me 1.6 times 10 to the 21. That's answer B. So a compound has an empirical formula that's noted here. What is the molecular formula? If the molecular weight is what it's shown as. So we just need to calculate the empirical mass. That's 12.01 times 5 plus 1.008 times 2 plus 14.01 times 2 plus 16 times 4. That's 154.09. 086, if you will. And so we're going to take the molecular weight, divide by the empirical, figure out how many of the empirical units are in the molecule. 462.243 divide by 154.086 works out to 3. Okay, so the formula should be C15H6N6012. Answer C. Moving on to 6. PbNO3, 2, and Ki are mixed. What is the maximum yield of PbI2? That may precipitate in grams. We're given some molar masses here to help us do the problem here. Okay, so BCA chart could be used. Problem with the BCA chart is this, is that I kind of should put moles in, makes the most sense. I start thinking minus x, minus 2x, plus 2x, etc. That I really should be plugging moles in here. I have grams, so I don't like BCA charts when we have grams, just because it's going to make me calculate things too often. So the problem-solving approach I'm going to do here is to say the maximum amount of PbI2 that can be made. Well, why don't I just start with 2? Why don't I solve for the grams of PbI2 that we can make using each of the reactants? 2.57 grams of the lead nitrate versus using all of the Ki. This, I think, dimensional analysis step is a much simpler approach for this particular type of problem. You can still solve it with the BCA chart. I just think this is going to be quicker. It might make a slight bit of more sense. So we're going to go 1.2 grams per mole of PbNO3, 2, and then the coefficients is 1 to 1. 1 mole of PbNO3, 2 that reacts produces 1 mole of PbI2, and then 1 mole of PbI2 has a mass of 461.0 grams. Okay, then for Ki, only difference for Ki is the molar mass is different, so it's 166.0 grams per mole of Ki, and then the stoichiometry is different. It's for every 2 mole of Ki that react, we produce 1 mole of PbI2, and then 1 mole of PbI2 equals the 461.0 grams, as noted above. So let's stop and calculate here. 2.57 divided by 331.2 times 1 divided by 1 times 461. Okay, so when we get 3.58 grams of PbI2, here what this quantity means is we can produce 3.58 grams of PbI2 if this quantity of lead nitrate reacts with the required quantity of Ki. So this assumes that we have enough Ki around to make this quantity. Now let's check the Ki and see how much product we can make with it. So we do 2.28. 2.28 divide by 166, then divide by 2 for the stoichiometry, and then multiply by 461 grams per mole of PbI2. That gives me only 3.17 grams PbI2. So now if Ki, the quantity given, reacts with the required amount of lead nitrate, then we would only produce 3.17 grams of lead iodide. So what this means is as soon as we make 3.17 grams of lead iodide, that we would have consumed all the Ki. This is now down to 0. This is kind of what I mean, where if you're thinking of a BCA chart, that you're losing this, losing 2 of these, you're making these as the reaction takes place, but that's helpful to think about what goes on, so we can know that this quantity is impossible to make, that when we make 3.17 grams, we've run out of Ki. We have no more Ki to give us the remaining amount of lead iodide we would get if we were to consume all the lead nitrate. So this is just a limiting versus excess reactant problem. So the limiting reactant here is Ki, and then the answer to the problem should be 3.17 grams, which is B. Question 7 is just looks like a balancing question. There's just some BS. So let's see here. Oh, no, I'm sorry, it's not. We have to balance and then work out a stoichiometry problem. My mistake. So we have sodium hypochlorite is being produced by this reaction below. Balance reaction and how much Cl2 is needed to react with 60 grams of sodium hydroxide. Okay, so we're going to balance this reaction. We got 2 hydrogens here, so maybe we need a 2 over here. We got 2 chlorines, 3 chlorines, so we're going to need, we got chlorine in 2 spots, so we're good on the chlorines. We have oxygen, 2 of them. I think we're in balance now. So we have 2 sodiums on both sides. So we can check the sodium. We can check the oxygen. We have 2 on the left side. We have 1, 2 on the right side. And then the hydrogen count, we have 2 versus 2. And then finally, the chlorine count, 2 versus 2 on both sides. Okay, so we're good. So just 1's in all these other spots. You don't necessarily have to write those in. But so then the question's asking the number of grams of sodium hydroxide, or number of grams of chlorine, that's what we're looking for, to react with 60.0 grams of NaOH. We just need to go to the molar mass. That's 23.00 plus 16.00 plus 1.008, so that's 40.01 grams per mole of NaOH. And then it's 2 moles of NaOH that require 1 mole of CO2 to be 1 mole of Cl2 to be present to react with it, and then 1 mole of Cl2 has a mass of 35.45 times 2, so that's 70.90 grams. So 60.0 divided by 40.01 divided by 2 times 70.9 works out to 53.2 grams. So 53.2 grams of chlorine reacts with 60 grams of sodium hydroxide. So when 14 moles of methanol and 24 moles of oxygen react, according to the combustion reaction, how much of the excess reactant remains once the reaction completes? Okay. So we could make a particle diagram. I think it's just too big of a count of molecules for that to be useful. So I might think BCA chart, 14 molecules of methanol, 24, oh, these are moles, not molecules. So let's rewrite. So methanol, we got 14 moles. Oxygen, we have 24 moles. And we could think we need a 3-to-2 ratio of oxygen to methanol, and right now, do we have greater or less than that amount? We'll just do 24 divided by 14 and see. We have greater than a 3-to-2 ratio, so we definitely have oxygen present in excess. Now we can check this with our BCA chart, because if oxygen is present in excess, then the methanol should be, let's do it this way, the methanol should be completely lost, so 2x minus 3x here. So methanol should go to 0 if oxygen's in excess, and then x is equal to 7 moles in that case. So we're going to lose 3 times 7 in the case of O2 and be left with 3 moles once the reaction completes. So the reaction completes, we're down to no more methanol, 3 moles of oxygen, then we've converted and formed 14 moles of CO2, and then plus 4x in the case of water, we formed 28 moles of water. once the reaction completes. Okay, so how much of the excess reactant remains? 3 moles of oxygen remains. Here we go, D. So we're given 1.23 grams of titanium chloride reacting with oxygen. According to the reaction below, yields this particular quantity of TiO2. What is the percent yield of the reaction? Okay, so this problem here, we might go to the percent yield that we're looking for is our actual yield, divide by the theoretical maximum yield, times 100%. That we already know the actual yield here is the 0.456. So we just need to figure out the theoretical yield. This is when we get using the stoichiometry. So we have the number of grams that we should get of the TiO2 would be equal to 1.23 grams of TiCl4. Then we're going to multiply that by the molar mass of TiCl4. So that's 47.87 plus 35.45 times 4. So that's 189.7 grams per mole of TiCl4, and then it's 1 to 1. And then 1 mole of TiO2 would be 47.87 plus 16.00 times 2, that's 79.87. Grams. Okay, so 1.23 divided by 189.7 times 1 divided by 1 times 79.87. That works out to 0.5178. 3 sig figs on it if you're counting. And so then we're going to take that quantity into here. This is the yield in grams. So take 0.456. Divide by 0.5178. So it works out to 88 point, to be accurate, I get 88.1, but 88.0 close enough for the answer. So 88.0 for the correct answer on this one. Okay, so final question here. We have a particle diagram that shows F2 and Cl2 in a container before the reaction, so I have 3 molecules of each. Now, which diagram shows what should be present once the reaction completes, where we're taking Cl2 plus 3F2 to 2 ClF3s? Okay, so let's try to make our after box. So the chlorines are these here. I need to take one of these and then all 3 of the fluorines together. Then when I do that, we're going to make one ClF3 and then a second ClF3. And then I'm going to be left behind with the Cl2s. Okay, so I should have the Cl2s left, 2 of them, and then 2 Cl3s. So it really looks like box A. Problem with box B is we don't have the excess reactant remaining. Product C has the wrong formula. That's not the right formula that we should be making. Same thing with D is not the right formula. And then E is just nonsense. That's just like doing some other reaction altogether. Okay, so answer is A for the last one. All right, thanks for the attention.